This is the video podcast for Chapter 3 of Hydrological Processes in Ecosystems, and the topic is the Basin-scale forest water balance. This first slide just presents the goals of this chapter, and in this video podcast, I'm only be going through part 1. There's two goals I'd like to present here. First, I want to introduce you to the energy balance concept at the watershed scale, and even though the title is Water Balance, we still need to address the energy balance. I'll be explaining that more. The other thing I'd like to do is to help you conceptualize the processes of evaporation, transpiration, and as part of transpiration, stem flow. If we look at a watershed, which is illustrated here, this is the same slide I had in the video podcast for Chapter 1, Part 2. And what you can see here is a three-dimensional control volume consisting of the land surface with a stream over it and some subbasins on it. We have the subsurface soil zone, which is shown here as weathered mantle, and then beneath that is the abrupt transition to bedrock. So for this control volume, or this watershed, we can write a hydrologic balance. This is the water balance, mass conservation. On input, we have precipitation given by the symbol P. That's all of the rain, snow, or other kinds of water moving from the atmosphere down to the ground. Then that is balanced by a combination of outflows, symbolized by Q plus ET, and then also GW out. And then there are also storage components, which can be plus or minus potentially, but SM, which is soil moisture, and then depression storage. So the outflow components are the discharge or stream flow Q, which is what's leaving the outlet at the point for which the watershed was designated. That may also include an underflow component, which is water moving through the soil or sediment under the stream. We've got evapotranspiration given by the symbol ET, and I'm going to be spending most of this video podcast addressing that. And then we also have the outflow of any groundwater that's moving down through the bottom boundary of this control volume, which is generally water that's moving through fractures between the soil and the bedrock. There's other ways it can move down as well, but let's just leave it there. There also is the storage terms, moisture in the soil itself. If the soil is usually part of the control volume that we were looking at with the water balance. So SM just means soil moisture. And then we have the depression storage. These are like ponds or lakes or even anywhere that the water is stored on the surface itself. Note that this is leaving out moisture that could be stored in biota, so or animals potentially, I guess. But that's not the focus right now. So we have this water balance. And what we really want to do is to try to understand this evapotranspiration term, because that's really the primary challenge. And the reason why that's such a challenge is because, as you're going to see, most of these terms can be directly measured as a water flux. It's theoretically possible to measure the water fluxes in evaporation and transpiration, but usually when you're looking at the watershed scale of the totality of that, it's often a lot easier to do that using an energy balance. And students find this particularly difficult because energy balances are not something that students get exposed to much in school. So this may be the first time you've heard of it or thought about it, or maybe the first time you're looking at it in depth. Evaporation is the process by which the phase of water is changed from a liquid to a gas. So that's not too complicated. I'm sure you're all familiar with that idea. In this illustration on the slide, there's a puddle on a road. So the water is ponded there. If we zoom in and look at it in cross-section, you can see the water in blue overlying the ground shown in orange and yellow. That puddle is being influenced by heat from the ground, because the road itself might be hot, as well as heat from the sun, which is shining down on that. If we zoom in very tightly and look at individual molecules at the water surface, like right at that interface, we'll see that their individual particles are being energized by the heat that's coming from the ground and from the sun. And as they're energized, then some of those particles are going to have a greater tendency to basically at random launch themselves or move from the water where it's majority liquid, into the air. And once it's in the air, then if there's any wind present, that wind can pick up that moisture and carry it away from the pond. Of course, some amount of water, these particles are going down into the water from the atmosphere, and others are going up. And it's all in the relative amounts that we see the net change. The important thing is that as this water is transferred from the surface into the air, we're also transferring energy, because there's the energy that is associated with the difference in temperature between that water particle and the air that's around that, or the water that's around that. So this leads us to then needing to think about the overall energy balance. Just that we had mass conservation that told us how much water could be moving, and we're using that in hydrology, we can also draw on an energy balance, and especially when we're looking at evapotranspiration. The concept here is relatively simple. The vast majority of energy from the Earth is coming from the sun. It's not all coming from the sun, and if you want to pause for a minute and just think to yourself, what might be a secondary source of energy for the Earth if not the sun? If you're not sure, you can also look it up. So imagine that we have 100 units of incoming radiation. That's just made up. It's not what that exactly is, but let's just say you start with 100 units of energy. More than half of that is either backscattered, reflected by clouds or surface, or absorbed by clouds or gases in the atmosphere. Only 46 out of those 100 units ends up in the ground. Meanwhile, energy in the ground is released to the atmosphere and space in a variety of forms. One is long-wave radiation, which is pretty much the same as it's entering. In addition to that, there's what we call sensible heat flux. Sensible means that you can sense it, which means you can experience it using our senses. And typically that's in the form of a temperature gradient. So when you feel a difference in temperature from the ground into the air, like if the ground is hot, then you're experiencing that. Hold on a second here. Okay, so then there's also shown here latent heat transfer. Now what is that? Well, latent heat transfer is energy that is in the water that is transferred from the surface into the air. And so you can see that relative to long-wave radiation and sensible heat, this latent heat transfer is a large number and very significant. I also want to point out there's actually a fourth term that's not shown in this NOAA diagram, which is direct conduction. So conduction is just when you have particles bumping into one another, energy can be transferred that way too, but it tends to be relatively slow at the ground-air interface. So if we take the ideas from this conceptual picture and turn it into an equation, we can write an energy balance this way. Now it's a little bit misleading because normally I like to write all the ins on one side and all the outs, but instead we have this term Rn, which stands for net radiation. So net radiation is the amount of long-wave radiation that's absorbed by the Earth minus the amount of long-wave radiation that's released from the Earth, and that's the net radiation. It's measured using a device called the net radiometer. And you can see there are these hemispherical plastic or glass, it looks like globes that are there. One is looking up and one is looking down. So what it's doing is it's looking at how much radiation is coming in from the top and how much is coming up from the bottom. And the difference between those two, it's like if you did a subtraction, that is the net radiation. The sensible heat flux is what you feel. It's going to be measured with temperature gradients. We'll talk more about that in a moment. The subsurface heat flux, this is the movement of heat upwards through the soil or from soil into the water or water into the air by conduction. One way to get at that is this thing called the heat flux plate. And then finally we have this term LE. Now these are independent variables, L and E, but together they have to do with evaporation. E is essentially the amount of water that's moved, and L is the amount of energy per unit of water that's moved. And together they yield an energy term. Now let's think about units for a moment. In this equation, we're talking about energy, and you may remember from Introduction to Physics that energy has the same units as work, which has the units of force over a length. If you take that and look at it as a rate, like force over length per unit time, then we tend to think of that more as a unit of power. But it's often thought of conveniently in hydrology as like a unit of energy, even though technically it's not. So the units of force times length are typically given the symbol J for joules, which is the SI designation for the units for energy. And if we have joules per second, then that would be the other option here. In hydrology, there's a relatively convenient method for looking at evaporation and trying to quantify it. It's called the Bowen ratio method. This is a method that's suitable when you're talking about something that you can measure over the ground surface or a crop canopy, or if you have a large enough crane, you can also look at it over a forest canopy. In this method, first let's just look at this weather station that we have here. Number one shows two instruments that are shown here in these white areas in the white circle. These two are separated by a distance of 1 meter, and inside of them are relative humidity sensors and temperature sensors. What we're doing here is we're measuring the difference in moisture and temperature at two elevations above the ground. And that's the key to the Bowen ratio method. So we can define this variable B as the ratio of the gradient in temperature to the gradient in moisture. So first, let's look at this term on the right. dT is the change in temperature. That's the division symbol, and then dQ. Now we have a little bit of a challenge in that different hydrologists use different symbols for water or water vapor. In this case, we're going to be using lowercase q to indicate water vapor, but sometimes you'll see the Greek symbol nu, and sometimes you'll see E or possibly even an epsilon. I mean, there's a variety of things. So this is the ratio of the gradient in temperature to the gradient in moisture. The other part of this term are constants. Cp is the heat capacity of air. So Cp times dT is telling us that for any gradient in temperature that we're having a transfer of heat associated with that temperature gradient. And heat, Cp is the specific heat capacity of air at a constant pressure, joules per kilograms of air and degrees Celsius. So we're pretty much saying that if we can specify this change in temperature, how much heat is being moved. L is the latent heat of vaporization of water. It tells us how much energy is held for each kilogram of water. Okay, so the Bowen ratio essentially is giving us the balance between the sensible heat flux and the latent heat flux. So if we go back, notice how this term has an H and an LE. So let's say for the moment that we eliminate G, because this conduction is a relatively small amount unless there's something unusual happening. So let's eliminate that and just look at H and LE. Well, since B equals H over LE, we can rewrite the equation this way. So we have net radiation equals the Bowen ratio plus 1 times LE plus G. So again, the Bowen ratio is H over LE. So B times LE is equal to H. 1 times LE is just LE. So let's assume that this is 0. So that means that if we can measure the Bowen ratio with this instrument and we can measure the net radiation with the net radiometer I showed you, then we can calculate for E because L is just a constant. So that's the idea of Bowen ratio, the method for directly measuring evaporation. But it's not that simple because, again, this is if you can look at it more or less as a point, and we can't. If we're talking about a forest scale, watershed scale water balance, we can't just go out and measure the Bowen ratio at one or two places. That's just crazy. We need a way to get to this at the watershed scale. So that's where we're headed, and that's really the topic of the second part of this video podcast. This shows a map of what mean annual lake evaporation is over a 9-year period. So in the United States, we went through this phase in the middle of the 20th century when it was really easy to instrument lakes to measure the bare, water evaporation, and you produce this nice map. And you can see that the dark blue, like particularly in the northern and northeastern states, have relatively low evaporation, whereas here in the very light blue in the southwest, especially in southeastern California, or possibly even in southern Texas here, this part of Texas, we can see relatively high rates of evaporation. And so it's no surprise that where you have high temperature, drier conditions, lower precipitation rates, you're going to have very high potential for evaporation. And if you have a lake, like a man-made reservoir, then you have an abundant source of water so you can fully realize that potential evaporation. Now, transpiration is a very similar process to evaporation. It's just that it's mediated by vegetation. So imagine a plant. It has three zones. It has a subsurface zone in the soil where its roots are located. It has its stem and branches, and then it has its leaves. So what happens is that water is taken up into the roots of a plant. It moves up through the plant and then ends up at the leaves. I'm going to talk more about how that process works, but first, just at this conceptual scale, if we zoom in at the small scale in the root zone, you can see that there are individual root hairs, and that's where water is absorbed into. Then the water shifts over into the xylem, which is the transportation part of the plant or wood, and the water basically can move up through the xylem, and it's translocated up eventually to the branches and the leaves. Inside the leaves, there are cells called stoma, which are here on the outside surface, and then just inside of those are air spaces, and then just beyond those are these spongy parenchyma. What you can see is that these air spaces create an opportunity for water to come out of the cells and potentially leave the tree by coming in contact with the atmosphere. So the process remains evaporative, it's just that it's mediated by the plants, and I'll show you how that happens. If we zoom in very tightly on the cells there, they're called the stomata guard cells. These are cells that actually control the opening to give either greater access for air that's in those air spaces, water that's in those air spaces to come in contact with the atmosphere or not. So the photo on the left shows an open guard cell, and the water is able to freely come out. On the right, it's closed, and so or relatively closed. And so, the plant has the ability, depending on the amount of moisture that's in the air and its status, to decide how open or closed it can be. When we look at the flow of moisture, we have something called Xylem Sap Flow. So this is the liquid flow through the plant stem that I was talking about. And so transpiration includes this sap flow component. What you see here is the symbol psi, and that's used to represent the water potential. If you've taken soil physics, you may remember the matrix potential. But if you haven't, that's okay. What this psi relates to is the ability of the atmosphere or whatever area you're in to suck or grab water. Essentially, what's the pull that's put on there? And so that's measured as a pressure in terms of the pressure units, which are pascals, or MPa, which is megapascals, which is millions of pascals. The units here are negative, which indicates a very strong desire for the plant desire for that component to get water. So if you think about soil, when soils are very dry, they have a very high potential for water, and so it's very strong. But if it's wet, then they have a relatively low potential because they already hold a lot of water. So what this image on the right is showing is a gradient in water potential from the soil zone where it's relatively wet soil with a very small value close to zero, and then you have this very, very strong desire in the atmosphere to get water. And it's this gradient that essentially drives the water, because water has, it's a liquid or it's a fluid, and all fluids flow from areas of high pressure to low pressure, in the absence of some other larger force. It's not important. But the main thing is most flows go from areas of high pressure to low pressure, and that's exactly what you see here. So it goes from the soil into the root, up to the stem, the branch, and the atmosphere, and you can see that the potential is getting stronger and stronger, which means it's deviating farther and farther from zero. Now that you understand that water flow through the tree is driven by a gradient in water potential, I can explain to you how we can take advantage of that to measure transpiration. What I really wish we could do is go to the leaves of the tree, to those air pockets, and actually see the evaporation as it's occurring. But of course, that evaporation is taking place over a very large number of leaves, so it simply doesn't make any sense to try to do that. You have to measure it in a more centralized location. Obviously, that centralized location would be where the whole tree is in one spot, and that would be in the trunk. So if we think about the flow of water through the xylem, we know that it's moving from the roots up to the branches, and we can insert a probe there and try to make a measurement. The way that's done is by taking advantage of the concepts of diffusion and advection in heat flow. So in this slot image on the screen, what you can see is a tree. Heartwood indicates the center of the tree, and then where it says sapwood, that's where the xylem is, that the water is flowing. These arrows indicate that the water is flowing up. So as the water is flowing up, we'd like to know what that velocity is. What we do is we insert a heating element at some location in the tree. Now in the absence of flowing water, if the water was just standing in the xylem, then as we apply heat to that heating element, you would expect the heat to be moving in both directions. Well, I should really go like this. It should be moving up and down, okay, equally. And so we would get like a bell curve of heat moving away from the heating element. But when you have a unidirectional flow, as just is illustrated here, that's going to start to move the heat in one direction, which is up. It will still be diffusing in both directions, but you have to now account for the second component. And our goal really is to measure that second component of the unidirectional flow. The term we use for that unidirectional flow when it carries something with it is called advection. So the way that this works is that as the heat is applied and the water is flowing, the heat is moving away in all directions, but predominantly more of it is moving up with the current than down. So then what we do is down from that, we insert something called a thermocouple. A thermocouple is a device that we use to measure the temperature. And so as the heat is applied, the diffusing heat will make its way down even against that flow and be sensed at the thermocouple. The amount of heat that you sense here is proportional to, or I should say it's inversely proportional to the velocity. So a very low flow would allow a lot of heat to move down against that current. So a high heat at the sensor indicates a low flow rate. If there was, of course, no flow at all, you would have the highest possible rate because you would basically set up a gradient and then that heat would be moving out. So as you apply more and more, as the flow increases more and more, it's pushing that heated water away and the gradient becomes more abrupt. So when you have a low amount of heat here, that has to mean that there's a really high rate of flow and relatively little heat is getting to the thermocouple. So in summary, sap flow measurement takes advantage of the idea of advection versus diffusion, and we have really good equations in fluid mechanics that can predict what the velocity must be for different levels of heat measured at different locations, given knowing how much you're applying at that source location. Okay, the last thing I want to show you is just some typical, real-world sap flow data. So this last slide shows two different plots. On the x-axis in both cases is time of the day from midnight to midnight over a one-day cycle. On the y-axis in the upper plot is the vapor pressure difference in the air. So remember that the vapor pressure difference, that's essentially the deficit of moisture that's in what could be taken up into the air. There's two lines here, sunny and rainy days, and on a particular day of the year. So on a sunny day, even when it's dark outside, you have a stronger vapor pressure difference because it's basically just hotter and there's less moisture in the air. But when you get in by midday, like noon, you can see a dramatic difference in the availability of the air to take up more moisture. And so you can see that difference here. On a sunny day, there's a lot of a vapor pressure difference, so there's a lot of potential to take up moisture. On a rainy day, there's always still, some capability there, unless all the air is fully saturated, but even on a rainy day, it often isn't. So that's the top plot. So then associated with that at the bottom is the sap flow velocity in millimeters per second. And you can see that on a rainy day, as that vapor pressure difference goes up, we're increasing the water potential gradient, and as a result of that, the sap flow velocity increases. So the sunny day has a significantly higher, more than 3 times higher sap flow velocity than on the rainy day. Okay, so that concludes this introduction to some basic ideas about evaporation and transpiration, and in the next video podcast, I'm going to explain to you how we estimate the totality of evapotranspiration at the watershed scale.